Your expert is Arthur T. Benjamin, the Smallwood Family Professor of Mathematics at Harvey Mudd College. He has served as president of the Fibonacci Association, and his teaching has been honored repeatedly by the Mathematical Association of America. His book, The Magic of Math, was a New York Times bestseller.
Behold my favorite numbers, the Fibonacci numbers. The Fibonacci numbers are literally as easy as 1 plus 1 equals 2. This is followed by 1 plus 2 equals 3, then 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. These numbers show up everywhere in the world of mathematics as well as the world we live in, and have some truly magical properties. The Fibonacci numbers were named after Leonardo of Pisa, later nicknamed Fibonacci, who was the greatest mathematician of the Middle Ages. Born around the year 1170, Fibonacci was the son of an Italian merchant who traveled with his father to the Middle East and Africa. It was there that he encountered the Indo-Arabic system of doing arithmetic, and he saw that it was vastly superior to the Roman numerals that were being used throughout Europe. Imagine trying to add, subtract, multiply, and divide using Roman numerals. It would be awfully clunky. On a recent trip to Italy, I had a chance to visit Fibonacci's statue in a museum next to the Leaning Tower of Pisa. Here I'm asking him the riddle, why was Fibonacci afraid of the number 5? The answer? Because 5, 8, 13. In 1202, Leonardo of Pisa wrote the book Fibonacci, the Book of Calculations, which taught the merchants of the Western world how to work with numbers the way we use them today. Like any decent textbook, Fibonacci was filled with hundreds of mathematical exercises, and one of these problems had to do with immortal bunny rabbits. The problem went something like this. Let us suppose that when a pair of bunny rabbits is born, one male and one female, that after 1 month, the female becomes fertile and produces another pair of bunny rabbits the following month and every month thereafter. And the offspring have the same mating habits. The question is, if a brand new pair of bunny rabbits enters your garden in January, then how many pairs will there be in December? So in January, we have one pair. Let's call them Adam and Eve. And we still have one pair, Adam and Eve, in February. But in March, that pair has a baby pair. Let's call those babies Anna and Steve. So there are 2 pairs now. In April, Adam and Eve have another pair, so now there are 3 pairs. In May, Adam and Eve have another pair, but so do Anna and Steve. So now there are 3 plus 2, that's 5 pairs. In June, all 5 pairs that were around in May are still around, since these rabbits never die. And the 3 pairs that were around in April have now had a pair of baby bunnies. So in June, we have 5 plus 3, which is 8 pairs. Continuing this process, we see that in month N, we have all the pairs from month N minus 1, plus all the babies of pairs that were around in month N minus 2. Hence, the numbers will continue to grow in leapfrog fashion. July will have 8 plus 5, that's 13 pairs. For August, we'll have 13 plus 8 is 21. September has 21 plus 13 is 34. October has 34 plus 21 is 55. November has 55 plus 34 is 89. And finally, December has 89 plus 55. That's 144 pairs of rabbits. These are the Fibonacci numbers, 1, 1, 2, 3, 5, 8, and so on. As we'll see in this course, the Fibonacci numbers are everywhere. Although inspired by an unrealistic problem involving immortal bunny rabbits, we'll see that they have other real-world applications, and they show up in nature surprisingly often. For instance, we'll see that for many flowers, the number of petals is typically a Fibonacci number. And when looking at pineapples, pine cones, and sunflowers, the number of spirals in each direction is typically a Fibonacci number. And we'll get a sense as to why this should be true. But for me, as a mathematician, what I love most about Fibonacci numbers are the amazing patterns they display. In this lecture, we'll explore many of these patterns, and in subsequent lectures, we'll explain all of these patterns and discover more of them along the way. So, here's our first pattern. Let's see what we get when we add the first few Fibonacci numbers together. For instance, what do we get when we add the first 10 Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55? The answer is almost staring us in the face. Let's look at some data and see if we can detect a pattern. Okay, now, if we add the first 3 Fibonacci numbers, we get 1 plus 1 plus 2, which is 4. The first 4 Fibonacci numbers, 1, 1, 2, 3, add up to 7. The first 5 of them, 1, 1, 2, 3, 5, add up to 12. If we add up 1, 1, 2, 3, 5, and 8, that gives us 20. Do you see a pattern? The numbers 4, 7, 12, 20, they're not Fibonacci numbers, but they are almost Fibonacci numbers. In fact, they're each 1 less than a Fibonacci numbers. The numbers 4, 7, 12, and 20, those were our totals, are each 1 shy of 5, 8, 13, and 21. In other words, when we add the first 3 Fibonacci numbers, we get 4, which is 1 less than the 5th Fibonacci number, 5. The first 4 Fibonacci numbers add up to 7, and that's 1 less than the 6th Fibonacci number, which is 8. The first 5 numbers, 1, 1, 2, 3, 5, they add up to 12, which is 1 less than the 7th Fibonacci number, and so on. In general, the sum of the first n Fibonacci numbers is 1 less than the n plus 2nd Fibonacci number. Remember when I asked for the sum of the first 10 Fibonacci numbers? I said the answer was almost staring you in the face. That's because the last number on our list was the 12th Fibonacci number, 144. So the sum of the first 10 Fibonacci numbers is just 1 less than that, which is 143. Now, just because the pattern works for the first few numbers, that's no guarantee that it'll work all the time. But in our next lecture, I'll give you several ways to prove, beyond a shadow of a doubt, that this pattern will persist forever. But we'll defer proofs for later. Let's look at some more amazing patterns now. Now let's look at the squares of Fibonacci numbers. Now, if we square the first few of them, we get 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, and so on. Now, when we add consecutive Fibonacci numbers, we always get the next Fibonacci number, right? That's how they're created. But you wouldn't expect something like that to work for their squares. But check this out. 1 plus 1 is 2. 1 plus 4 is 5. 4 plus 9 is 13. And 9 plus 25 is 34. 2, 5, 13, 34. These are all Fibonacci numbers. The Fibonacci numbers are everywhere. Or here's another one. Suppose you add the first bunch of Fibonacci squares starting from the beginning. What do you get? All right, let's look at some data. 1 plus 1 is 2. 1 plus 1 plus 4 is 6. 1, 1, 4, 9 add up to 15. 1, 1, 4, 9, and 25 add up to 40. 1, 1, 4, 9, 25, and 64 add up to 104. Do you see a pattern? 2, 6, 15, 40, 104. Now, these are not Fibonacci numbers, but if you look at them closely, you can see the Fibonacci numbers buried inside of them. Check it out. 2 is 1 times 2. 6 is 2 times 3. 15 is 3 times 5. 40 is 5 times 8. 2, 3, 5, 8. Who do we appreciate? Fibonacci, of course. Yeah, check out the next one. 104, that's 8 times 13, just as we predicted. All right, here's another fun pattern. Take the square of any Fibonacci number, say 5 squared, which is 25. Now take that Fibonacci number's neighbors and multiply them together. Here the neighbors of 5 are what? 3 and 8. And their product, 3 times 8, is 24, which is almost 25, right? 25 and 24 differ by 1. Let's do another example. 8 squared is 64, and 8's neighbors, 5 and 13, multiply to 65. Again, they differ by 1. And this pattern apparently goes on forever. But that's not all. Suppose we look at the neighbors that are 2 away. Here, the neighbors that are 2 away from 8 are what? 3 and 21, which multiply to 63, and that's still 1 away from 64. Here, let's look at the number 13, whose square is 169. Now, the neighbors that are 1 away have a product of 8 times 21, that's 168. That's 1 below 169. And the neighbors that are 2 away from 13, let's see, that's 5 and 34, those multiply to 170, and that's 1 above 169. What if we look at the neighbors that are 3 away or farther? As we'll see in a future lecture, there is still something very interesting that happens. Maybe you can spot the pattern now, but let's move on to another odd property, or maybe I should call it an even property. My question is, which Fibonacci numbers are even? All right, well, looking at our list, we see the even numbers 2, 8, 34, 144. These occur in positions 3, 6, 9, and 12. It's tempting to conclude that every third Fibonacci number is even, and you would be right. In fact, we can prove this property right now. Notice that the Fibonacci sequence begins with numbers 1 and 1, which are both odd. So the pattern begins odd followed by odd, so their sum must be even. Next, we have odd plus even, which is odd. Then even plus odd is odd. And now we're back to the starting point with 2 odd numbers. And their sum, of course, will be even. So we start off odd, odd, even, odd, odd, even, and this pattern goes on forever. Odd, odd, even, and so on. Thus, every third Fibonacci number is even, and the rest are odd. What if we look at every fourth Fibonacci number? Starting with the number 3, we have 3, 21, 144, 987, and so on, all of which are divisible by 3. And indeed, every fourth Fibonacci number is a multiple of 3, and the rest are not multiples of 3. The same sort of thing happens if we look at every fifth Fibonacci number, 5, 55, 610, and so on. Every fifth Fibonacci number is a multiple of 5, and in fact, they are the only multiples of 5. Likewise, every sixth Fibonacci number is a multiple of 8, and they are the only multiples of 8. And the pattern continues. Every seventh Fibonacci number is a multiple of 13, every eighth Fibonacci number is a multiple of 21, and so on. By the way, this pattern, if we believe it, tells us something interesting about prime Fibonacci numbers. What can we say about the 66th Fibonacci number? Well, since we know, or at least we believe, that every sixth Fibonacci number is a multiple of 8, then that means the 66th Fibonacci number has to be a multiple of 8. It also has to be a multiple of the 11th Fibonacci number, 89, but the point is, since it's divisible by 8, it can't be prime. Applying this logic means that aside from the prime number 3, which is the fourth Fibonacci number, every prime Fibonacci number must be in a prime position, right? For example, the prime Fibonacci numbers 5, 13, 89, 233, and 1,597 occur in prime positions, namely the 5th position, the 7th, 11th, 13th, and 17th positions. It would be tempting to conjecture that all Fibonacci numbers in prime positions must be prime, but this pattern breaks down. For instance, even though the number 19 is prime, the 19th Fibonacci number, 4,181, it might look prime, but it's not prime. Specifically, 4,181 is 37 times 113. In fact, even though there are infinitely many prime numbers, only a few dozen prime Fibonacci numbers have been discovered. For example, even though there are 1,229 prime numbers below 10,000, if we look at the first 10,000 Fibonacci numbers, only 26 of them are prime. The question remains, are there infinitely many prime Fibonacci numbers, or is it a finite number? The answer is nobody knows. It's an unsolved problem in mathematics. If you could prove or disprove the statement that there are infinitely many prime Fibonacci numbers, you would achieve instant fame in the mathematics community. By the way, it has been shown that among the Fibonacci numbers, there are only 2 perfect squares, namely 1 and 144, which is 12 squared. And there are only 2 perfect cubes, namely 1 and the cube of 2, which is 8. And these proofs appeared only in the last few decades, relatively recently in the history of mathematics. For our final pattern, let's look at what happens when we divide consecutive Fibonacci numbers, okay? Here, let's look at some data. I'm going to take Fibonacci numbers and divide it by the Fibonacci number before it. So 1 over 1 is 1, 2 over 1 is 2, 3 over 2 is 1.5, 5 over 3 begins 1.66. 8 over 5 is 1.6, 13 over 8 is 1.625, and now check this out. 21 over 13 begins 1.615. 34 over 21 begins 1.619. 55 over 34 begins 1.617. 89 over 55 begins 1.618. 144 over 89 begins 1.6179. 233 over 144 begins 1.6180. What we see here is that these quotients are getting closer and closer to some number that is approximately 1.618. More specifically, as we go further and further in the Fibonacci sequence, the consecutive ratios are getting closer and closer to the number 1.61803398887, a remarkable number known as the golden ratio. In fact, we will devote the entire second half of this course to the golden ratio, highlighting its mathematical properties and its appearance in geometry, art, nature, and the world around us. Indeed, just like the Fibonacci numbers, the golden ratio is everywhere. But in this course, I don't want to just present you with amazing facts. I want you to actually appreciate the reasons behind these amazing patterns. Why do these numbers have all the beautiful properties that we've seen, and why do they appear so often in nature? To understand this, we developed some tools in the next few lectures that will allow us to prove, beyond a shadow of a doubt, that the patterns that we've seen, through just a handful of examples, will be true forever. And I assure you that when the light bulb goes on and everything makes sense, it's an amazing feeling. Finding the patterns is a great deal of fun, and understanding these patterns can be even more satisfying. I'll leave you with these words that sum up my feelings about mathematics. Mathematics is not just solving for X, it's also figuring out Y. Welcome to the world of Fibonacci numbers and the golden ratio.